Chapter 8 in Section 1, the law of sines. So there is a proof to go through for these. I am not going to do that in the video. We are going to have to just accept the law of sines. If ABC is an obtuse triangle, labeled in the usual manner, which we'll rediscuss in a few minutes, then you can take the sine of alpha over A is going to equal the sine of beta over B and the sine of gamma over C. Or you can flip it around and take A over the sine of A, alpha, equals B over the sine of beta, which also equals C over the sine of gamma. The law of sines can be used on an oblique triangle. An oblique triangle is one that does not contain a right angle. And it can be used whenever we know the following. When we have two sides and an angle opposite one of them. So this would be your side-side angle. Or if we have two angles and any side, so either angle-angle-side or angle-side-angle. Let's look at example 1. Solve triangle ABC, given that alpha is 48 degrees, gamma is 57 degrees, and B is 47 units. So please first pause the video and draw the picture of this. So up above, when we talked about labeled in the usual manner, we're talking that the side A is going to be opposite angle alpha, side B is going to be opposite angle beta, and side C would be opposite angle gamma. So we have our triangle labeled. Again, we're not going to worry about labeling it or having it be to scale. And hopefully you recognize this is a triangle, so you remember that we can easily find angle B because this angles of a triangle have to add up to 180. So if we take 180 minus the two angles that we know, we find that angle beta is 75 degrees. I've written off to the side everything that we need in order to solve the triangle. Remember from previous chapters, solving a triangle means finding all the missing parts. So we need to know what all the angle measures are. We have those now. And we need to find what all the side lengths are. So we need to still find side length A and side length C. So let's use the law of sines. A over the sine of 48 degrees equals 47 over the sine of 75 degrees. Multiplying both sides by the sine of 48 and putting this into your handy-dandy calculator, you should get that A is 36.15 units. We're going to use conventionality, which basically says everything is given in terms of whole numbers, so I'm fine with you giving your solution to this in whole numbers. This would round to approximately 36. We're going to do the same thing for side C. So C over the sine of 57 degrees equals 47 over the sine of 75 degrees. And as I stated earlier in a previous chapter, again, when possible, use information that's given in the problem rather than information that you are calculating. And again, when we put this into our handy-dandy calculator, we find that C is 40.81. So rounded correctly, we would say that side length C is 41. Also, when you're doing these, make sure that your calculator is in the correct mode. If it's been in radian mode, to solve these problems, you need to put it in degree mode. All right, now let's consider alpha is an angle in standard position. I've drawn this all over here. Segment AC has length B on the terminal side of A. So remember, the x-axis is the initial side of our angle. The third vertex B is going to be somewhere on the x-axis. And there are four possibilities that can happen depending on the side length of A. So first of all, I could have this side length of A, and no matter how I swing this side length of A, the arc does not intersect the x-axis. If the arc does not intersect the x-axis, what does that mean? Well, that means we can't have a triangle. We're going to call this our case 1. Second of all, second thing that can happen is that the arc is tangent to the x-axis. In other words, it's the shortest distance. So that shortest distance would be directly down to the x-axis, which means my angle B is going to be a right angle formed. We're going to call this our case number 2. The third thing that can happen is that the arc intersects the axis at two distinct points. So it's long enough that it could intersect there, or it could intersect there. So there could be two triangles formed. We could have this triangle of ABC, or we could have this triangle of ABC. We're going to call this case 3. And our fourth case, the arc intersects both the positive and non-positive parts of the x-axis so that only one triangle is formed. Because remember, this has to be our initial side. So if I have a really long arc, okay, it's going to extend over there. It could also extend back that direction. But then if it extended back this direction, this would not be my terminal side. So we still really only have one triangle formed. And so that's case number 4. And so now let's look at how this impacts, how do we recognize which one of those 4 cases we have when we're solving a triangle. So which case occurs will become evident, should become evident when a solution is attempted. So while you're solving this or one form of this, if you get that the sign is greater than 1, if you think about the sine wave or the unit circle, the sign can't be greater than 1. So if you end up with a sign of beta or alpha or gamma is greater than 1, then no triangle exists. Second of all, if the sine of beta equals 1, then that means that beta is a 90-degree angle, and case number 2 applies. And if the sine of beta is less than 1, either case number 3 or number 4 applies. For case number 4, if alpha is greater than 90 degrees, then a triangle can only exist if and only if side A is bigger than side B. So here I have the example drawn. If this is my side B, side A is opposite angle alpha, this would obviously have to be longer than side B in order for a triangle to exist. And in case number 3, since there could be more than one possibility, given 2 sides and an angle opposite one of them, this is called the ambiguous case, and you must find both triangles. So for example 2, again, I would like you to pause the video and draw the triangle. A lot of times with these problems, drawing the triangle helps an incredible amount to be able to set up the problem. So as I set this up, I can see that I have an angle and a side opposite, and I have a side, but I don't have that angle. So I am going to solve for the sine of gamma over 125 equals the sine of 67 over 100. By multiplying both sides by 125, I'd like you to go ahead and solve this for the sine of gamma. When you solve this, you should get that the sine of gamma equals 1.15. Again, the sine can't be greater than 1, so in this case, there is no triangle. Example number 3. Again, I would like you to pause the video and draw the triangle that represents the given information. Again, I have an angle and a side, and I have a side and a missing angle. So again, I can use the law of sines. And I'm going to write the sine of 36.7 over 8.7 equals the sine of alpha over 12.4. So again, I would like you to pause the video and solve this for sine of alpha. We get that the sine of alpha is 0.8518, and so remember, other than quadrantal angles, there's always going to be 2 angles that have that same positive value. So go ahead and find what those 2 values would be. So to find my first angle, alpha is the inverse sine of 0.8518. When I plug this into my calculator, I get that my alpha is 58.4 degrees. And then remember, 58.4 degrees is there. My other positive sine angle is going to be in the second quadrant, so it's going to be 180 minus the 58.4 degrees. Gives me my second angle is 121.6 degrees. So we're going to call this one alpha sub 1, and my other angle in my ambiguous case, alpha, is going to be alpha sub 2 is 121.6 degrees. Now for the first triangle, we still need to find what gamma 1 is, and we also need to find what side length C1 would be. Well, remember gamma we can find because we take 180 minus the 2 angles we know, 58.4 and 36.7, and we're going to get our gamma is 84.9 degrees. And now we can use our law of sines. We can say that C over the sine of 84.9 equals, we want to use our given information, so 8.7 over the sine of 36.7. Popping all this into your handy-dandy calculator, you should get that C1 is 4.5 units long. Similarly, over here, our gamma 2 is going to be 180 minus 121.6 minus 36.7. So we get that our gamma 2 is going to be 21.7 degrees. And when we use our law of sines here, c over the sine of 21.7 equals 8.7 over the sine of 36.7, we find that our C2 should be 5.4 units long. Example 4, when the angle of elevation of the sun is 64 degrees, a telephone pole that is tilted at an angle of 9 degrees directly away from the sun casts a shadow 21 feet long. Please pause the video and draw your picture. So this is what I have for my picture. The angle of elevation, remember your angle of elevation is from the horizontal, so it's 64 degrees. And the telephone pole is tilted directly away from the sun, so this is my 9-degree angle off of that vertical. And I need to find out how long is my telephone pole that casts this 21-degree shadow. So this 9 degrees is off of the vertical, so I can say that this angle, I'm going to call it alpha, is 81 degrees. Therefore, using the fact that 180 minus 81 minus 64 is 35 degrees, I know that this angle up at the top is a 35-degree angle. And now I can use the law of sines. If I, just for namesake, call that side B, so then my side B over the sine of 64 equals 21 over the sine of 35. Popping this into your handy-dandy calculator, we find that B is 32.9, so we could say that our telephone pole is approximately 33 feet long. I do not want to rush through these last two problems that deal with the directionals, so I'm going to pause or stop this video now. If you understand what we're doing with the law of sines, I would encourage you to at least try these last two problems and check in with the addendum video that I'm going to post. Otherwise, I will see you in class.